To understand chemistry is to solve a puzzle. Why a piece of coal and a breath of air combine to form something entirely new. Every element on the periodic table interacts according to a rigid mathematical blueprint. By the end of this session, you will be able to apply the first foundational law of chemistry to balance and solve complex reactions like a laboratory chemist. All chemical combinations are governed by 5 major laws. These 5 laws dictate the exact mathematical boundaries for any reaction. They determine what percentage of one element will react with another, how many moles are required, and how gases will divide their volume ratios. A mole is a standard scientific unit used to measure large quantities of very small entities, like atoms or molecules. Scientists established these rules between the 1740s and the 1780s. Because these rules are centuries old and mathematically proven, mastering them is the first step to solving any modern chemical equation. We begin with the most foundational rule, the law of conservation of mass. This law states that mass can neither be created nor destroyed during a chemical reaction. Think of a chemical equation as a physical scale. On the left are the reactants, the starting materials. On the right are the products. To work, the scale must perfectly balance. The total mass of reactants must equal the mass of the products. This proves that matter cannot simply vanish during a reaction. It only changes form. We can test this law using a simple reaction, burning carbon in the presence of oxygen to create carbon dioxide. Here is the skeletal equation. Carbon plus oxygen yields carbon dioxide. Carbon's atomic mass is 12, oxygen is 16, but with 2 atoms, this reactant totals 32. Adding 12 and 32 gives a reactant mass of 44. The resulting carbon dioxide molecule also totals 44. Since both sides equal 44, the mathematical proof is complete. The law holds firm. While these rules are reliable for laboratory chemistry, modern physics has identified a specific scenario where the math changes. Albert Einstein introduced a discovery that shifted our understanding of mass and energy. In certain high-energy nuclear reactions, the law of conservation of mass is technically bypassed. This manuscript shows the specific equation, E equals mc squared. This proves that mass can be converted directly into energy. During these specific reactions, a tiny amount of mass is released as energy, which slightly tips the mass balance on the product side. Despite this atomic exception, the classical law remains the standard for every reaction you will perform in a standard chemistry lab. Let's apply this framework to a more complex challenge. Combustion is a chemical reaction between a fuel and an oxidant that produces heat. Ethane is a colorless, odorless gas often used as a fuel source. Suppose you conduct a complete combustion of 1.5 grams of ethane, which produces 4.4 grams of carbon dioxide and 2.7 grams of water. We place our known masses under the ethane, the carbon dioxide, and the water. Note the blank space under the oxygen reactant. Oxygen is often the silent variable in these equations. Because it's a colorless gas pulled from the surrounding air, it's easy to overlook its physical mass when balancing the reactant side. By treating the equation as a balanced scale, you can now find the missing mass of the oxygen. This framework allows you to prove mass conservation in any experiment. Complete the calculation in your notes before the next lesson.